Let's talk about some theorems about continuity and differentiability. Here are two versions of the same theorem. It says if a function is differentiable, then it is continuous. Another way of saying that same thing is that if a function is not continuous, then it is not differentiable. Logically, this is something called the contrapositive. It goes like this: if A implies B, so if A implies B, then we can turn that around and say not B implies not A. So this works for any if-then statement. If A, then B is the same thing as saying if not B, then not A. You can turn it around backwards and then put nots on there, negate the things, and it still works. If it's sunny outside, I'm going to go for a bike ride. I'm not going for the bike ride, so it's not sunny outside. Right? Something like that. So in this theorem here, what we have is the original statement about a function being differentiable, and then we have the contrapositive. So these are just two sides of the same coin. Here's an abbreviated version. Differentiable implies continuous, not continuous implies not differentiable. So this leads us to three instances in which a function is not differentiable. A function is not differentiable at a point A if f is not continuous at A, we already know that. F has a corner at A, and f has a vertical tangent at A. So let's look at why that's the case with just some very simple examples. If f is not continuous at A, well, we might have something like this. How about this? And we'll do an example after this too. That's not what I wanted to say. How about this? So if we're looking at this situation, see the discontinuity there. If we're looking at the tangent lines, on the left we have a slope of about 1, but on the right we have a slope of -1. So at this very point A, is the derivative 1 or -1? We can't say. So if a function is not continuous at that point A, there's no way to talk about the derivative there. The second instance is if f has a corner at A. And by corner we just mean something like this. Let's see. Something like that. If we're approaching in from the left, we have a negative slope here, but if we approach from the right, we have a positive slope here. Whoa. So which is it? Is it the negative derivative or the positive derivative? Well, we can't say, so it doesn't really work at a corner. And the vertical tangent is also problematic. By that we mean something like this. The function's coming along happily, and then it goes straight vertical here, and then keeps going. Right? Even if it's just for a single point. A lot of times it's just for a point, but the tangent line right at this point is perfectly vertical. Right? So when that happens, you might say, whoa, it's an infinite derivative, but is this positive infinity or negative infinity? Right? We can't say, so the function is not differentiable at that point. So keep these three cases in your back pocket just for a quick reference on when a function is not differentiable. And let's do an example. Okay, so part A, find the values of x in 0 to 3 at which f is not continuous. Okay, well, I'm seeing a jump discontinuity at x equals 1. So at x equals 1, we have a jump discontinuity. I'll just say jump. Okay, part B says find the values of x in 0 to 3 at which f is not differentiable. Well, we know anywhere it's not continuous is automatically not differentiable. So we have 1 here, and we also know it's not differentiable at a corner. So here I'm going to say x equals 1. It's not continuous there, and we know that it's not continuous. It can't be differentiable, and we also have 1 at x equals 2 because that's a corner. Okay, part C asks us to sketch a graph of f prime. So the way we do this is we look at specific points in the original graph and look at the slope of the tangent line, and that helps tell us what the derivative is. So here, right at the origin, it looks like that slope goes to about 0. So then our derivative, so this graph over here on the right is f prime of x. So f prime of x is 0 at the origin. But then note in our original function here, by the time we get to 1, our slope is about 1. So here's m equals 1, before it was m equals 0. Right, we're looking at the slope of the tangent lines of those things. So we have something at 1 here. Now I'm using an open circle because the function is not differentiable at x equals 1. And then we connect the dots like so. Okay, now I'm going to jump across here and look at this top line here, this top part of the curve. And it looks like to me that is basically a horizontal tangent line again there. So it looks like we're picking up at m equals 0 again. And now we're going down, and by the time we get over to 2, our slope is about, I don't know, I'm going to say -1. Right, remember, perfect diagonal is either 1 or -1. Okay, so now we're down to -1, and again, I'm going to use an open circle here because it is not differentiable at 2. Back to the original graph, as soon as we get over this corner and go to the other side, I draw my next tangent line right on the other side of this corner. Suddenly I'm up at 1 again. So this tangent line has a slope of 1. Okay, so now we're back up at 1. And then it looks like it just stays at 1. So it stays constant here. Looks like it goes just flat out. Right, because this just stays the same slope. So the slope of that is 1 across, all the way across. So that's our graph of the derivative there. Right, 3 lines basically. Now you may be saying, why isn't it open circles here at the endpoints too? Well, we're only considering this thing on the open interval 0 to 3. If that was a closed interval, then I'd be drawing open circles at the end of this. But since we're only looking at 0 to 3, it's actually okay to not include those open circles there. You could dig down pretty deep to determine why that's the case. But how about just taking my word for it for now and not including those open circles?